Hello everyone. Today we will introduce one fundamental model for modeling share prices, that is Black-Scholes model. For that we need to first study what is meant by an Ito process. Okay. So we have studied Ito integral. We know it's an integral with respect to Brownian motion. So on the basis of that we are now going to define Ito process. So Ito process is basically a stochastic process which would involve some function of Brownian motion and it satisfies certain conditions. So let me write down the definition. Let Zt, where small t is between 0 to capital T, be a standard Brownian motion. So we would generally use this same notation for standard Brownian motion, that is Zt. With respect to its natural filtration. Okay, so with natural filtration Ft, I hope you remember what is meant by natural filtration. Ft is again defined on the same interval. Then Ito process is a stochastic process. Ito process is a stochastic process of the form, so it satisfies certain form. Let me write down xt. So xt is an Ito process if it satisfies this form. Xt is x naught plus integral 0 to t a xu u du plus integral 0 to t b xu u dzu. Okay, so this is u. Okay, so there are a couple of things. First, we are saying that xt is an Ito process if it can be expressed in this form. So what does this form consist of? See, this is a usual integral because this is just du. This is Ito integral. Okay, so first thing, only this part is Ito integral. This is usual integral. So this is usual integral means this is kind of deterministic integral. In integral there is no randomness. Okay, and then a and b are some functions. They are bivariate functions. So their inputs are the process and the time component. Okay, so a and b are certain functions, and actually because just now I said that in this part time is not random. Time we know progresses in a set fashion, deterministic fashion, whereas z is random. So this kind of contributes to variance of the process. There is no contribution to variance from this first part. Okay, so this contributes to mean of the process. Okay, so that's why this a and b would have names called as drift parameter and variance parameter. So let me first write the differential form and then we'll write down these names. So this is known as integral representation of the Ito process. Okay, so this, whatever we wrote here, this is known as integral representation of the Ito process. There is a differential representation also, so let me now write that. So what is differential representation? So we write dx as a xu u du plus b xu u dzu. Okay, see, xt minus x naught is like change in x, so we wrote it as dx, and then in the other two factors integral sign is gone. So we have this differential representation. So as we mentioned earlier, this part doesn't have anything random. So this A is known as drift parameter because it contributes to mean of the process. Okay, drift or shift. And this B is known as variance parameter because of this Z there is a randomness, so this is going to contribute to variance. Okay. So this is a differential equation. So I hope you have studied differential equations in mathematics. So this is a differential equation, but this is not an ordinary differential equation. It does have a randomness coming in picture, right? Z is a stochastic process. Hence, this is known as stochastic differential equation. Okay, or SDE. And just like given a usual differential equation, you try to find if there is any function which satisfies that. Similarly, here also we try to find solution to this stochastic differential equation, and this solution would exist only under certain conditions. So let me write those conditions down. So A is a function of x. So let me write now small x. X of u I am denoting by small x. So A is a function of x and t, and B is also a function of x and t. So A and B are defined on r cross 0 to t because the stochastic process can take any real value. So r cross 0 to t. And further suppose that they satisfy Lipschitz condition. You remember Lipschitz condition from calculus? Further suppose that they satisfy Lipschitz condition. What is the Lipschitz condition? That is, there exists L greater than 0, of course, such that mod of axt minus ayt is less than or equal to L times mod x minus y. So with respect to the first argument, they satisfy Lipschitz condition, Lipschitz continuity, and bxt minus byt is less than or equal to L times mod x minus y. Now whether you have to have a common L, see, you can have different L's, but then you can take maximum. So you can always have a common L. Okay. And if x0 is given to be independent of zt, the initial value, okay, is given to be independent of zt, then, so if these conditions are satisfied, then this stochastic differential equation that we mentioned above, let me maybe give some number to that equation or name. Okay, so let me say this is equation star. Okay. So under these conditions, means if A and B are Lipschitz continuous and if x0 is independent of xt, then star has a unique solution. Okay, so this star admits a unique solution. So there exists a process which satisfies that differential equation, and that process is unique. Okay, and that process we will call as Ito process. Is it okay? Now let us take an example so things would be more clear. How do A and B look in, such processes? So we want this type of representation. We want dx to be a du plus b dz. So let us take one simple example. So let ST be stock price at time t. Stock price, I hope all of you remember, it's a share price. Stock price at time t, and expected rate of return is constant. Expected rate of return is constant. Now what do I mean by rate of return? Return you measure as relative return. Okay, so delta S upon S, change in S with respect to the original S, this is constant. Okay, so it can be written as delta S is equal to delta S by S is equal to mu, and of course the return is with respect to time, so delta T is there. Okay, so this is ds equal to mu S dt. With this delta, when you write, this is known as discrete representation, and when you write ds dt, this is known as continuous representation. Okay. Now if I write ds equal to mu S dt, then I know I can do ds by S as mu dt. This is your, if you remember your differential equation from mathematics, this is variable separation, right? You have S on one side and T on other side. And if you integrate this, so if you try to find solution, you have to integrate it. So ds by S over 0 to T is mu integral dt over 0 to T, because mu is of course constant. So this becomes ln of st, because ds by S I would get log, minus ln of s naught as mu t. So this is st equal to s naught e raised to mu t. Okay, st equal to s naught e raised to mu t. So if the return is constant, if it is not random, then you can actually have a nice equation for computing stock price at time t in terms of original stock price. Okay, because it's not random. If you remember, this is nothing but what would be value at time t if mu is like rate of interest. When we had continuous compounding for interest, this is exactly what we got. Okay, so in such a case, this kind of investment, investment in this particular stock would be profitable if mu is greater than r, right? Because if you are getting return more than the risk-free rate of interest, then only this investment would be profitable. Otherwise, you could very well invest in a bank. Okay. Now this is so this is one example, and now on the basis of this Ito process, we are going to introduce Black-Scholes model, which is a very celebrated model in finance. Okay, so Black-Scholes model is a very celebrated model. So in general, of course, we know that the stock price process has to be random. It can't be derived only by a constant. So we'll add one more term for randomness. So ds equal to mu S dt comes from what we saw earlier, and for randomness we will have sigma S dz. Okay, so dz would bring in randomness, sigma is the variance parameter. Of course, you can write the discrete version as delta S by S as mu delta t plus sigma delta z. Okay, and we know something about Brownian motion. What do we know? That quadratic variation of Brownian motion we have computed. Okay, so that using that we will write delta z as epsilon times root delta t. Okay, why? Because we know that dz square means variance of Brownian motion is actually same as the time lag. Variance of increment of Brownian motion is actually same as the time lag. Okay, so using that we are doing this substitution, and we will take epsilon as normal 0 1. Why? Because we know z is a standard Brownian motion. Okay, so epsilon is normal 0 1. As a result, what we would have? we would have variance of delta S upon S, variance of delta S upon S when I try to compute. First term is not going to contribute because there is no randomness. I'll have sigma square variance of delta Z, correct? And what is variance of delta Z? Variance of delta Z we know is delta T. Okay, so because Z you can write as ZT minus Z naught, and then that variance is the change in T, etc. We can also write the same thing in the integral form. So integral over ds 0 to t is same as mu integral 0 to t s du plus integral 0 to t, sigma can stay outside, s dzu. Okay, so this becomes st minus s naught as mu times integral 0 to t su du plus sigma times integral 0 to t su dzu. This is known as integral representation of the Black-Scholes model. Okay, so integral representation of the Black-Scholes model. And now from this earlier differential representation, we can say something about the probability distribution. Okay, so we can see here delta S by S, this part is constant, and this Brownian motion we know has normal distribution. So overall delta by S will also have normal distribution. Okay, so let me write that. So I can write delta S by S has normal distribution. Mean would come from the drift part mu delta t, because Brownian motion has zero mean, and then sigma square delta t. Okay, so this will have normal distribution with this mean and this variance. Okay, so far? Okay, let us take one small example. So suppose we have a stock which pays no dividends. Stock which pays no dividend. So, and we know something about, say, mean and variance parameter. So volatility is 30% per annum. Volatility is actually your sigma, and expected rate of return is suppose 15% per annum. Expected rate of return is suppose 15% per annum. So in our notation, mu is 0.15 and sigma is 0.3. Okay, sigma, not sigma square. That is important. Okay, then what can we say about the distribution? So we will write the Black-Scholes equation. So ds is 0.15 s dt plus 0.3 s dz, correct? So this becomes the equation, and now using this we can find distribution of stock price at any given time point. So suppose I want what happens after 1 week. So if t is 1 week, 1 week I can write as 1 by 52 of year. So 1 by 52 of year means it will be 0.0192. Then delta S by S would be, now mu into dt is now 0.0192. So if I substitute that, I get 0.00288 plus 0.0416 times epsilon. From where this has come? Because again for dz we are going to substitute in terms of epsilon square root delta t. Okay, epsilon square root dt. Got it? So dz is epsilon root dt, and dt is this, we know. Okay, So now I know distribution of the return because epsilon is normal 0, 1. So using this I can get, say, confidence interval for return, I can get expected return, etc. Is it okay? So okay, so I have a Black-Scholes model for, say, S, but I may be interested in some functions of S, right? Because sometimes we may be interested in prices of the derivatives and not just the stock price. So in that scenario, we are going to need model for functions of S. So we need a way of going from this equation which is for S to an equation for function of S. And that's where Ito's lemma will come into picture. Okay, Ito's lemma would help us go from a model from for S to model for any function of S. Okay, so let me write down the statement first. Let xt be a solution to stochastic differential equation, that we wrote earlier. So that is dx is equal to a xt dt plus b xt dzt. Okay, this was the original Ito process equation. So xt is a solution to this, and now we want to talk about function of xt. Okay, so let g x t be a twice continuously differentiable function. It has to be a well-behaved function, then only we can say something. So let this be a twice continuously differentiable function on r cross 0 infinity, because x can take any value in r and then t can take positive values. Then g follows the following stochastic differential equation. G follows the following stochastic differential equation. What is the differential equation followed by g? G is a function of x. X follows some equation. So then g follows this. dg equal to dabba g by dabba x evaluated at xt t times a xtt plus dabba g by dabba t evaluated at xtt plus half dabba 2g by dabba x square evaluated at xtt into b square xtt. This curly bracket closes. You have dt outside the curly bracket plus dabba g by dabba x again evaluated at xtt times b xtt dz. So what does this mean? This means that G is also an Ito process, but the mean and variance parameters are changed. Why am I saying it's an Ito process? Because it is again of the form something times dt and then something times dz. Okay, but this big thing becomes the mean parameter and this becomes the variance parameter. Okay, original process had A as mean parameter and B as variance parameter. Now I have this big thing in the curly bracket as mean parameter and this thing as variance parameter. Okay, how do we get this? This is actually application of Taylor's series or your delta method from asymptotic. So I won't go into the details, we don't need the derivation, but if you are interested you can try to use delta method or Taylor series expansion and you would get the values. Okay. Now let us take one example. So we will try to find differential equation for a function of a stochastic process. So we know Zt is a standard Brownian motion. And so let us take Zt itself as my original process. So xt is Zt and we are interested in finding equation for Zt square. So my g is basically a square function. Okay, so g is xt square. Okay, xt square means here it would be Zt square. We have to use the given form. First, let us write equation for original process. Now, dxt is dzt. Correct, because xt is zt. That's what we are taking here. So, what would be a and b? I want it to be, what we need is a is something in the mean plus b is something in the variance. Okay, so here I don't have a. So, a is basically 0 and variance parameter is 1. Okay. So now I know a is 0, b is 1 and now we will have to find other terms which we need. So we need dA by g by dA by x. So derivative of x square with respect to x, so it would be 2x. dA by g by dA by t would actually be 0 because there is no directly t involved, t is only through x. So partial derivative with respect to t is 0 and dA by 2g by dA by x square would be 2. So I have these values and now we have to substitute in this equation for Ito process. So dA by g by dA by x, a is anyway 0 so it won't contribute, plus half times we will substitute these things. Okay. So what do we get? We get dg as 0 plus half into 2 times dt plus 2 zt dz. Okay. So basically we get that z square t follows an Ito process with mean parameter as 1 and variance parameter as 2zt. So actual variance rate, if you take sigma square, then 4z square t. Okay. So variance rate sigma square if you want, then 4z square t, because this is just sigma. Okay, this is just sigma and mean is 1. Okay. Okay. So I'll stop here. Thank you.